Hi, and welcome to my first video on polar coordinates. In this video, I'm going to define polar coordinates, and then we're going to have a look at some conversions between polar coordinates and Cartesian coordinates. So first of all, let's jump into a definition of polar coordinates. And we're going to start by looking at this point P here in two-dimensional space on my XY plane. And let's look at our familiar definition of this point. We first of all describe how far across this point is from our reference point, which we call the origin. And then the second number is how far up we move from our reference point to get to our point P. And these two numbers, x and y, uniquely define the point P in the xy plane by telling us how far across we move to the right and then how far up we move from our reference point. Polar coordinates similarly uses two numbers to describe a point in 2D space, which really is required because it's two dimensions. So the two numbers, however, are defined quite differently. So the first number is how far away is that point from our reference. So the reference in polar coordinates is not called the origin anymore. We call it a pole, or the pole. So that's the polar coordinates equivalent of the origin. And r, this number here, that describes how far away our point P is from O. Typically, we would say r is non-negative, so r is greater than or equal to 0, although we can have negative r, and it does make sense to do so. So we will look at that in this video briefly, and then a bit more detail later on. The second number that we need alongside r is theta, and theta is the angle anti-clockwise from the positive real axis, and a typical value of theta would range between 0 and 2 pi, but this is not necessarily the case. I might say it's usually the case. Theta might go past 2 pi. It might make sense to go round and round a little bit rather than just going around the pole once. You just keep going and you get different parts of the curve. Or maybe it's going to be defined between minus pi and pi or something. So just pay attention to the context of the question. But principally, we would say theta is between 0 and 2 pi. So now every point on our xy plane can be defined uniquely by a value for r and a value for theta. Moreover, if you have a value of r that's non-negative and a value of theta between 0 and 2 pi, that will give you a point in the 2D plane. With one exception, the pole itself, theta is not defined at the pole. Okay, r is 0 at the pole, but theta is not defined at the pole. The pole tends to be a little bit of a crushing point in polar coordinates, but it's a sacrifice we make for what polar coordinates has to offer us. So what we can do to convert between polar coordinates and Cartesian coordinates is consider that this is a right-angled triangle here. So we can apply our right-angled triangle rules to it to convert between x, y, oops, didn't put the y on the axis there, x, y, r, and theta. So looking at this triangle, we can say that x, which is this base length here, that is going to be equal to r times the cosine of theta. And similarly, y, which is going to be this length here, that's the opposite, that must be equal to r sine theta. It's also a right angle triangle, so we can apply Pythagoras. So we would have this length here, which is x squared, plus this length here, which is y squared, and that will equal r squared, which is the hypotenuse. And then the last one, we can say tan of theta. So again, back to SOHCAHTOA. Tan of theta is the opposite, which is going to be y divided by x. And we would usually say tan theta equals, rather than theta equals arctan of y on x. Just because the arctan function is limited, it'll only give an answer between minus pi on 2 and pi on 2, whereas in reality, we probably want an answer between 0 and 2 pi. So this statement is true for all points x and y. So yeah, those are conversions. There's 4 of them. You do need to know them. They are quite straightforward, and each one omits one of the letters. So this one omits a y, that one omits an x, that one omits a theta, and that one omits an r. We tend to use these two to convert from Cartesian to polar form, and we tend to use these two to convert from polar form to Cartesian form. Okay, so that's the definitions of polar coordinates. Where we have x followed by y in a bracket, what we would do in polar form is we would have r followed by theta. So a number for r followed by a number for theta. So in that order, just like x then y is convention for Cartesian, r then theta is convention for polar. Okay. Example number 1. So we're first of all going to look at converting coordinate points. So what I recommend doing is just drawing a quick little sketch, particularly going from Cartesian to polar, because getting that angle theta is key and quite easy to get wrong. You don't want to make silly mistakes. So drawing a little sketch really helps to visualize exactly what's going on. So to get the value of r, we're going to use Pythagoras on these two numbers. So 5 squared plus 12 squared square rooted, well, that's going to be 13, because that forms a Pythagorean triple. 5, 12, 13. And then to get the theta value, well, that's going to be this angle here. We're going to use the arctan function, and that's just going to be the arctan of y on x in this case, because we're in that first quadrant, so there's no issues with the arctan function there. So that's going to be 12 on 5. Notice I'm in radians. That's quite typical for polar coordinates, just because we will be using calculus on polar coordinates later. So being in radians is good. 1.176. So that's the theta value. So this point in Cartesian looks like that in polar coordinates. Okay, we can do something similar for the next part. Minus 6 eighths, so that's going to be there somewhere-ish. Doesn't need to be too accurate. It's just to give me an idea of what theta value I'm going to be expecting. So my theta value here is going to be outside of the range of the arctan function. So I'm going to need to put some kind of correction in there. So what I'm going to do is, just like I would perhaps for an argument, I'm going to calculate the arctan of the y on x, which in this case is going to be 8 on negative 6. And then because that would give me an answer down here, I'm going to add pi to that to correct the issue that the tan function struggles with. So that's going to be the theta value for this this Cartesian coordinate. And as for the r value, well, 6, 8, 10 is another Pythagorean triple, so that's a nice integer again. So minus 6 squared plus 8 squared, all square rooted, is 10. And that was 2.214. 3 sig fig or better is fine, unless the question says otherwise. Okay, part 3. So 2 minus 2, that's going to be positive 2 that way and then 2 down that way. So it's going to be somewhere on this kind of 45-degree angle downwards. And because I've moved 2 that way and 2 that way, then this is going to be quite simply 2 root 2. So 2 root 2 goes there. And the argument, well, that's minus pi on 4. I said argument, it's not really an argument. The theta value, minus pi on 4, but that's not in the range, so I need to add 2 pi to that to go all the way around. So that's going to be, what did I say it was, pi on 4? So 7 pi on 4. Okay. And then the last one, 0 minus 5. Well, on my coordinate axes, I'm not moving in the x direction, I'm moving down by 5, so I'm down there. That is a distance of 5 from the pole, so the r value is 5. And then the theta value, well, that's going to be that angle there, which is going to be 3 pi on 2. And if you try to use the arctan function, you would end up dividing by 0, so it wouldn't work. So just make sure you've got some idea of the geometry that's going on, because actually once you draw that geometry, it's quite easy to spot that it's 3 pi on 2. Okay, conversions the other way. These are a little bit easier because x and y are defined quite explicitly in terms of r and theta. So x is r cos theta and y is r sine theta. So it's nice and easy to go from polar to Cartesian coordinates as opposed to Cartesian to polar where you've got to faff around with the theta values. So in this case, r is 2, theta is pi on 4. Don't even need a calculator for that one. We are going to get root 2. Okay, so I'm just plugging in r and theta into these two to get my x and y coordinates. Okay, Right, this one here, theta is 3. That's okay. It's an integer. It's not a pi. That's all right. It's still a valid argument. So I'm going to get 6 cos theta for my x-coordinate. So 6 cos 3 minus 5.940 to 3 decimal places. And then the y-coordinate is going to be 6 sine 3. So 6 sine 3. And that's 0.847. Okay. This one here, argument is 3 on 2, sorry, I keep saying argument. Theta is 3 on 2, 3 pi on 2, r is 1, so cos of 3 pi on 2 is 0, and sine of 3 pi on 2 is minus 1, so that's negative 1 on the y-axis. For this one here, we have a negative r value, but that's okay, the maths can actually cope with that. It does make sense to have a negative r value, it just stops that kind of unique definition of every point on the xy plane. So we can still use these formula, it still does work. So we're going to get negative 2, and then the theta value was pi on 3. So cos of pi on 3. And that's going to give us minus 1 on the x-axis. And then we can plug in minus 2 sine of pi on 3, and that's going to give us negative root 3 on the y-axis. So geometrically what's going on here is, given the pole and x over there, pi on 3 would typically be along this line here, because that angle in there would be pi on 3. So if we have an r value up there with pi on 3, then it will be somewhere along this line. But because r value is negative, we extend this line past the pole and we just keep going down this way. And this is now at negative r value. So negative r being negative 2 means we're looking at down here. So the actual value of theta is going to be that angle there, which is going to be 4 pi on 3. So the principal coordinate, the principal polar coordinate of that point should be written as 2, 4 pi on 3. It's the same point, but because we've got a negative r value, we've lost that and a unique definition of every point on the plane. So it's still valid. It's not commonly used, but we do see r values that are negative a bit more when we look at graphs. So we'll see that in upcoming video. And then 5 of 13 pi on 4. Again, 13 pi on 4 is going to be out of range, but it just means you've just gone around the pole a couple of times before you actually land on your point that you're trying to get to. Again, plugging in 5 into here and 13 pi on 4 into here, we're going to get minus 5 root 2 on 2 and minus 5 root 2 on 2. Okay, so that's converting between polar coordinates and Cartesian coordinates for points. We're also going to have a look very briefly at converting between them for graphs as well. So we're going to look at converting from Cartesian to polar, first of all, because that's the easier way round, because we can directly substitute x is equal to r cos theta and y is equal to r sine theta. So we just lift up those definitions and put them into the equation here. So the top one there is going to be a circle. So let's have a look at what we get. We're going to get r squared into cos squared of theta plus r squared into sine squared of theta, and that's going to equal 25. We can factorise out the r squared. That'll leave a cos squared plus sine squared, which is 1. So we get r squared is 25. And if you square root that, because we know r is positive, we'll get r is 5. So that's the equation of the circle in polar coordinates, which makes sense. That's going to be a circle centred on the origin with a radius of 5. And that's just going to represent all of those points that are exactly 5 away from the pole to the circle. Part 2. X times y equals 6. So we're going to get r squared cos theta sine theta is equal to 6. So we can rearrange that just to make r squared the subject. And what I'm going to do is I'm going to use a double angle formula as well, just to tidy that cos theta sine theta up. So I'm going to say that this is going to be equal to r squared times sine of 2 theta is equal to 12. And that tells me that r squared is going to be 12 cosec of 2 theta. Okay, I'm going to leave it as r squared is that, and if the right hand side happens to be negative, then the curve wouldn't exist. Part 3, we've got y is equal to some constant. So that's graphically that's going to be a horizontal line that cuts the y-axis at the point A. And I'm just going to replace y with r sine theta. So r times sine of theta equals a. That tells me that r equals a times the cosec of theta. So this equation, r equals cosec theta, that is the equation of a horizontal line. Now that's good to kind of have in your head because we will come across those. So that's a horizontal line. So if you can recognise that that's a horizontal line, then that's brilliant. Okay. And then the last one, we've got x squared minus 6x plus y squared plus 8y equals 0. That looks to be like some kind of circle perhaps, maybe some hyperbolic curve, probably a circle though, that goes to the origin. Okay, so again, just like the previous 4 cases, we're going to lift up our definition of x and y in terms of r and theta. So x squared, that's going to be r squared times the cosine of theta minus 6r times the cosine squared, the cosine of theta, plus y squared, which is r squared sine squared of theta, plus 8y, which is 8r sine of theta. And that's going to equal 0. We can then divide by r. I mean, you are kind of considering that r is, you're almost ignoring that r is 0. But r is 0, I think we'll still cut the curve. We'll check that in a minute. So we'll divide the whole thing by r, just putting into the side of my head that r is 0 is a solution to this equation. And then I'm also going to combine the r squared cos squared and r squared sine squared to get r squared, but divided by r. So then I'm going to get r minus 6 cos theta plus 8 sine theta is equal to 0. And that tells me then that r is going to equal 6 cos theta minus 8 sine theta. And that's the Cartesian equation. Sorry, that's the polar equation of this curve. What you'll notice is as I went through those examples, I made the substitution in, and then in each case, I made r the subject, or maybe r squared for this case. And that's normal. Just like in Cartesian coordinates, we usually have the situation where y is a function of x. So as you vary x, we look at how y goes up and down. In polar coordinates, we tend to have r as some function of theta. So as you roll around the pole, how far are we moving in and out away from the pole? That's how polar coordinate shapes tend to work. Okay, so r is your dependent variable, and theta is your independent variable. Just like y is your dependent and x is your independent, which is a bit of a shame that we end up doing x, y. We have independent followed by dependent, whereas in polar we have r theta, which is dependent followed by independent. So just be really careful with that. This is convention. This is the right way around. R theta. Okay, so that's example 2. That was going from polar. That was going from Cartesian to polar, which is the easier way around. But we also need to be able to go from polar coordinates to Cartesian coordinates. And the relationships we have are r squared is equal to x squared plus y squared. And tan theta is equal to y divided by x. So I recommend getting rid of the thetas first, and then getting rid of the r's. Yeah, well, we'll see how it goes. But yeah, thetas tend to be a bit of a pain to get rid of because of this funny definition of theta. And you can't just say theta equals arctan of y on x, because you can't have a trig function of an arctan. You've got to simplify that algebraically. So the algebra can become a bit messier. So part I, there is no theta, so nice and straightforward. R can just be replaced with the square root of x squared plus y squared. And then we can square both sides. So x squared plus y squared equals 1. Technically, this is a semicircle, and then we squared it to make a circle. So we've kind of gained solutions going from there to there. But going from here to here, we actually lost solutions by square rooting in the first place. So this is the full circle. So we should have the full circle as our answer. So we've not introduced any phantom part of the curve. We have actually stated that the whole of the original curve going from here to here. What we could have done is started with squaring it and then going straight from there to the answer. Okay. Second one. Sec theta. Well, what I'm going to do is I'm going to just draw this triangle out here, which defines my theta. So theta is there, tan theta then is y on x. That means that must be a y, that must be an x. And we know that's an r. So when we have sec theta, sec of theta is going to be the hypotenuse divided by the adjacent. So that's going to be r on x. So when we come to do an answer for part 2, we can replace sec of theta with r divided by x by looking at this right angle triangle setup over here. Now we're going to end up with an equation that looks like r is equal to 4 times r divided by x, and then the r's cancel and we can times by x. So we end up with x is equal to 4. So just like when we had a cosec in the previous example, here we've got a sec. The cosec gave a horizontal line. In this case, the sec will give a vertical line. All right. Again, it's good if you recognise that. R equals something times sec theta is a vertical line, and R equals something times cosec theta is a horizontal line. Part 3. R equals a cos theta. Again, I'm just going to go back to this triangle one more time and use definitions of SOHCAHTOA to get rid of the cos theta. So the cosine of theta, well, that's going to be actually 1 over sec. So that's going to be x divided by r. So that's going to give me r is equal to a times x over r. That tells me that r squared equals ax, but r squared is x squared plus y squared. So now I've got r squared, and there's no thetas, I can get rid of the r squared, and I can conclude that the equation of this is going to be x squared plus y squared equals ax. And that's the Cartesian equation of that. Okay, so that's the first 3. The next one, part 4. R equals b tan theta sec theta. Again, just going to look at this, and I'm going to use this to eliminate my trig functions of theta. So in this case, I'm going to get b times tan of theta. Tan of theta is y on x. And then sec of theta, that is r on x. Now I've got this, it's got no thetas in it. I can divide by the r, and I can times by the x squared, and that's going to give me y is equal to 1 over b times x squared. So it's just a parabola which goes through the origin. And finally, part 5. For this one, we've got r squared equals cos of 2 theta, and I've got a triangle which has a theta in it. So what I'm going to do is I'm going to use a double angle formula first of all to get rid of the 2 theta and then replace the sines and the cosines with correct ratios from over there. So that's going to give me r squared is equal to 2 times sine theta cos theta. But sine theta, that's going to be opposite divided by hypotenuse. So that's y on x, sorry, y on r. And then the cosine of theta, that's adjacent by hypotenuse. That's going to be times x on r. So that's then going to give me the equation r to the 4 equals 2xy. And now that all of my thetas have gone, I can replace the r. And this is r squared squared. So that tells me that I'm going to get x squared plus y squared squared equals 2xy. And that's the Cartesian equation of that polar curve. Okay. I'm just looking at my notes over there, and that's not what I had. So just let me check that I've done that one right. Oh, it was cos of 2 theta. That's silly. I did r squared equals sine of 2 theta, so I replaced it with the wrong trig identity. So that's actually an incorrect answer. So let's change the question. And then let's redo that last one. So let's do a part 6 down here. R squared equals the cosine of 2 theta, which is what the question should have been. So that tells me that r squared is equal to cos squared of theta minus sine squared of theta. Cos squared is x squared on r squared. Sine squared is y squared on r squared. So that tells me that r to the 4 equals x squared minus y squared. And then I can replace the r squared just like I did before. So that's x squared plus y squared squared equals x squared minus y squared. There we go. That's what I had on my sheet. Okay, so yeah, that's very much an introduction to polar coordinates and conversions between polars and Cartesians. In the upcoming videos, we're going to have a look at some polar shapes. I'm quite excited about those. They look really cool. And then we're going to have a look at some polar coordinate calculus towards the end of the course. So thanks very much for watching. As always, if you have any questions, please just drop them in the comments and I'll get back to you when I can.